Hello everyone, hope you're all doing fine. I came back with another lecture on electrostatics. In the previous lecture on electrostatics, we have learned about three different types of charge densities: linear charge density, surface charge density, and volume charge density. In this video, we are going to learn some of the examples in which we use linear charge density. So yes, my name is Vijay Krishna and you're watching Office channel. Let's get started. Okay, let's look at this case. In this case, we are going to find the electric field due to this charged rod at a point on the axis of the charged rod. So this is the charged rod, let's say, which is positively charged, Okay, you can even take negatively charged also. The concept and the steps are all same, except the direction changes. Okay, direction reverses. For positive charge, it is away from the charge. For negative charge, it is towards the charge. Okay, now this is a positively charged rod of linear charge density lambda. But here I'm going to recollect the definition that we have learned in the earlier lecture. Linear charge density. Linear charge density is defined as charge distributed per unit length of the object, which we have already learned in the earlier lecture. Okay, so linear charge density. Linear charge density formula also we have learned in the earlier lecture as Q by L, charge per unit length. This can also be written as small elemental charge per small element of length. Okay, dq by dx. I'm rewriting this equation for dq. dq is equal to lambda dx, which we use in the further expressions. Okay, right. Now what I'm going to do is I'm going to consider a point on the axis of the rod along its length. Now, next step is the length of the rod is L. Length of the rod is L. Now, what I'm going to do is I'm going to divide this entire rod into small pieces of small length dx. As the rod is aligned along the x-axis, I've taken the small elemental length as dx. If it has aligned along the y-axis, I would have taken dy. It makes no difference. So dx, the charge on this rod is dq, element is dq, which we have considered at a distance x from the point of interest. And as we already know, the electric field due to the positive charge is always away from the positive charge at the point of interest. Okay, this is our point of interest where we are going to find the electric field due to this entire rod, but before that, due to this small element. Now I'm going to write the equation for the electric field due to this small element only. As I've already mentioned, I've been mentioning multiple times, this is a small element, very teeny tiny small element. Okay, that means we can consider the small elemental charge as a point charge. Okay, so I'm going to write the electric field due to this point charge as dq, I mean de, is equal to k dq by x square. Okay, as we already know, as we have charge q and we are asked to find the electric field at point p, at a point p at a distance r, then the field formula is k q by r square. Same expression goes here. Okay, so same expression that I have used here. Electric field due to small element is dE is equal to k dq by x square, where x is the distance of the point of interest from the point charge, small element. Okay, now this dq can be written as lambda dx because charge is not given, whereas linear charge density is given. So I'm going to rewrite this equation as k lambda dx by x square by x square right. So this is the expression for the electric field due to the small element. But if I want to find the electric field at point p due to the entire rod, then what am I supposed to do? I have to integrate. De is equal to k constant lambda constant dx 1 by x square. Total electric field will be, okay, integration of the expression. So this x value can be extended over the entire rod, right? From here to here, this distance I'm assuming it as a, let it be a. Okay, that means the x value is extended from a to l plus a to l plus a. So the integration limits will be a to l plus a for for x, and the integration limits for de will be 0 to e, 0 to e. I hope the limits that I have taken are understandable, right? Right. So why I have taken 0, which is nearly 0? As I've taken a small element here, let's say I've taken small element here, the electric field due to small element here is negligibly small, not the entire rod, not due to the entire rod. As I'm adding all the elements, the electric field keep on increases, which will be considerable, at this point. At this point field is 0, at this point field is something, at this point field is increased, at this point field is further increased, at this point field is even more increased, at this point field is maximum, at this point field is maximum. Okay, this is how integration works, right? So how did I get this? One moment. Okay. Okay. K lambda 1 by x square dx, right? Okay. Now d. So if I apply the limits and integration formulas, this will be e minus 0 we will get, but however it is e. Now coming to the next one, k is constant. I'm taking that constant outside. Lambda is also constant, which is uniform. I'm taking that as well outside of the integration. 1 by x square dx, integral a to l plus a 1 by x square dx, 1 by x square dx, right? Now k lambda 1 by x square integration will be minus 1 by x, from where to where? A to l plus a. If you are unable to remember the formula, if you are unable to recall the formula, I am going to write it over here. Integral x to the power n dx is equal to x to the power n plus 1 by n plus 1, where n is 10, x to the power minus 2, that means n is minus 2, minus 2 plus 1 is minus 1, minus 2 plus 1 is minus 1, that means minus 1. X to the power minus 1 can be written as 1 by x, so minus 1 by x, l plus a, l a to l plus a. If I use the limits, first I'm going to substitute upper limit, so minus minus k lambda 1 by l plus a minus 1 by lower limit, minus 1 by lower limit. Now the final expression will be e is equal to, if I multiply this negative sign, what am I getting? K lambda 1 by a minus 1 by a minus 1 by a minus, what is it? 1 by l plus a. This is the equation for the electric field due to the charged rod along its length, at a point along its length. Okay, right. So what is the direction of the electric field? As I've already mentioned, direction is pointing away from the rod, away from the rod, pointing away from the rod. The formula will goes the same for the negative charge also, negatively charged rod also, but the direction reverses. That the electric field is towards the rod, towards the rod. I hope the entire explanation of the steps that I followed are clear to you. If you are unable to follow, just comment below. If you really like the video is helpful, I mean if you really feel the video is helpful, please do comment, like and share, subscribe. Okay, now let's move on to the next example. Okay, and one more point that I wanted to mention. The linear charge density that I've taken here is uniform. It is not changing with the length. The linear charge density lambda value is lambda here, lambda here, lambda here, lambda here, lambda everywhere along its length. It is not changing with its length or time. It is not a variable. Okay. So for such example, this is it is always best to remember this formula. But what if you are not given with a uniform linear charge density, rather you are given with a variable charge density? That means charge density is varying with respect to the distance, x length. Okay, in such case this formula will not work. Will not work. The key point to crack any competitive exams like JEE, NEET, BITSAT or BIT or any kind of competitive exam. The main key points that you need to remember is you have to remember the formulas to make to solve the questions faster, but not all questions can be solved with just a simple formula. Okay, some questions requires conceptual analysis. Okay, that's where you need to remember the analysis that we have followed. Even if you are given with the variable linear charge density, the process would remain same. The process would remain same. Let me give you an example. Okay, let's say you are given with linear charge density lambda is equal to 2x. Lambda is equal to 2x coulomb per meter. Coulomb per meter. Okay, if you look at this expression, as x changes, as the length changes, the value of lambda changes. For such cases, this formula will not work. Will not work. For such cases, you need to follow the entire procedure here. Okay, you need to substitute k lambda. Here we have k lambda is nothing but 2x, 2x. Again we have x square here, x square here, and dx, and dx. X will get cancelled. 1 by x, 1 by x. The integration of 1 by x will be log x, log x. That means you'll get log x here. You'll get log x, log L plus A minus log A. That means log A minus log B. Log A by B you can write log L plus A by log A. Log L plus A by A. You'll get a different expression if you are given with different lambda values. Okay, unless you are given with uniform linear charge density, you are not supposed to use this formula. When you are given with uniform linear charge density, then you are happy to use this formula, where A is the distance of first end of the rod from the point of interest, and L plus A is the distance to the second end of the rod from the point of interest, where L is length of the rod and lambda is the linear charge density. K already we know, which is Coulomb's constant. I hope the entire explanation is clear to you. Okay, if it is okay, then let's move on to the next example. Okay, this is another kind of example where we use linear charge density. Okay, again I'm going to write the linear charge density definition that I've already mentioned. Linear charge density definition is charge distributed per unit length of the object. Linear charge density formula lambda is equal to q by L, which is equal to dq by d y. Here I am going to take dy because the rod is along the vertical axis, y axis. Okay, so I am going to consider the elemental length as dy. Now I'm going to find the electric field due to this rod. Okay, I'm going to consider this rod is positively charged again. Positively charged again. Okay, now I'm going to consider a point. Let us suppose, let's take the linear charge density of this rod is lambda. Again, linear charge density of this rod is lambda. Okay, sorry, linear charge density of this rod is lambda. It is again a finite rod. Again a finite rod. I'm going to consider a point somewhere here. I'm going to consider point P here, where I need to find the electric field due to this rod. Okay. And now the rod is extended at different angles to different edges. From here, from here, sorry, from here. Okay. So let this angle is theta 1. Okay. And from here to here, let this angle is theta 2. Okay, so the rod is extended at angles theta 1 and theta 2 from the point of interest. Okay, now 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 what I'm going to do is, like I did in the earlier case, I'm going to consider a small element. That element is somewhere here. That element is somewhere here. Okay, so this is our element. This is our element where this element length is dy. Element length is dy, which is at a distance y. Which is at a distance y. Which is at a distance y. Okay, let us suppose this length is a. This length is a. Okay, from rod to point P, perpendicular distance is a. Now, now the charge of this element is dq. Charge of this element is dq. Okay, now what I'm going to do is, how did I take this element? I went to an angle theta. I went to an angle theta. Okay, I went to an angle theta, and I have considered a small element with an angle d theta. With an angle d theta. With an angle d theta. D theta means it's a small arc length. Small arc length. Circular arc length. Okay. Now, okay, let's go with the equational part again. Now, this small element can be considered as a point charge. Can be considered as a point charge. Now, due to this point charge, the electric field at this location will be, okay, electric field at this location will be dE, small electric field. Small electric field. Okay. So this dq is very small. Dq is very small, which is giving small amount of electric field at the point of interest, which is pointing away from the rod, as the rod is positively charged. And as we all know, electric field is a vector quantity. Electric field is a vector quantity. We cannot add the vectors directly. Rather, we use their component to add, or we can add them vectorial, right? So if this angle is theta, then this angle also will be theta. If this angle is theta, then this angle also will be theta, right? Now, this dE can be resolved into two components. One component goes here, which is dE cos theta. One component goes here, which is dE sin theta. dE cos theta and dE sin theta. I hope the steps and the diagram that I have drawn here, or the steps that I have followed here, are clearly understandable. Okay, right. Now, now, okay. So this is the electric field due to the small element. Due to the small element, right? Now I'm going to write the electric field due to the small element. dE is equal to K dq by distance. This distance, let us suppose this distance is r. This distance is r, where r square, right? Now what I'm going to do is, I'm going to find this r, and I know the dq is equal to lambda dy. Dq is equal to lambda dy. So I can write k lambda dy upon r square. I don't know R, but I can find R in terms of known quantities like A and Y. If you look at this, diagram, this is the right angle triangle. Right angle triangle. If I have the right angle triangle, something like this, A, theta, and Y, this is R. How can I write the R expression? So if I write the tan theta is equal to Y by A, then Y is equal to a tan theta. Y is equal to a tan theta. I can find a dy, differentiate this y, dy by d theta. I am differentiating this expression with respect to theta. A is constant. Sorry, not sine theta. It is tan theta. It is tan theta. Sorry, tan theta. Tan theta differentiation is secant square theta. Secant square theta. If I rearrange this equation, dy is equal to a secant square theta d theta. A secant square theta d theta. This is one part. This is one part. Okay, I need to remember this dy is equal to a secant square theta d theta. And look at one more, from this right angle triangle, I can write this r square is equal to y square plus a square. Y square plus a square, right? Right? Okay. Now y is how much? A tan theta. Y is how much? A tan theta. Then this r square is equal to a square tan square theta plus a square. Theta plus a square. If I take a square common, what am I getting? 1 plus tan square theta. 1 plus tan square theta. And I know 1 plus tan square theta is nothing but secant square theta. A square secant square theta. A square secant square theta. I don't need the entire analysis, but I wanted to show you how I arrive at these results. Okay, so I use this simple right angle triangle to arrive at these results. Now I'm going to use these results in this expression. Okay, right. Now, so if I use these results in this expression, what am I getting? K lambda dy is nothing but a secant square theta d theta. A secant square theta d theta divided by, what is it? R square. R square is nothing but a square secant square theta. A square secant square theta. A square secant square theta. Once we write this equation, I'm going to wipe these two steps off. Okay, hope you have got the clarity how we arrive at these two results, right? And we are using these two results in the known expression for electric field due to small charge. Okay, clear? Right. Let's move on to the next step. Let's take these two things off. Sorry. Right. Right. Okay. Right. Now what do we left with? Secant square theta gets cancelled. 1a get cancelled. What are we left with? This electric field due to small element is k lambda by a into d theta into d theta. So this is the expression for the electric field due to the small element. Due to the small element. Now I have two components here. I have two components here. I'm going to divide this into two parts. So dE, I'm going to name this component as dE perpendicular because this is perpendicular to the length of the rod. Perpendicular to the length of the rod, dE perpendicular is equal to dE cos theta. dE cos theta, and I have what here? dE parallel. dE parallel because it is parallel to the length of the rod. So dE parallel is nothing but dE sin theta. dE sin theta, and I already know the expression for dE. Expression for dE. Expression for dE. So what I'm going to do is I'm going to write this relation somewhere here. K lambda by A d theta. This is the expression for the electric field dE here, and I'm going to take this off and I'm going to write this equation right here. dE perpendicular is equal to dE cos theta. That's it. Now let's go with the analysis. Okay, I know the dE expression, which is k lambda by a d theta is there. Here we have cos theta d theta, which is nothing but dE perpendicular. dE perpendicular, right? Now angle is changing from perpendicular line to the negative side and the positive side. To represent such negative angle and the negative measurement of angle and positive measurement of angle, I have mentioned the arrows here. Okay, below clockwise, I mean counterclockwise, above clockwise. So anyway, I'm going to use the integration here. This integration goes with the limits of angles, right? Now this angle is nothing but, when you go below it is negative minus theta 1, and when you go above from the vertical line, that is theta 2, right? And this entire thing goes like perpendicular component. E perpendicular is equal to, k is constant, lambda is constant, a is again constant, cos theta integration is sin theta. Cos theta integration is sin theta, and we have the limits minus theta 1 to theta 2. Minus theta 1 to theta 2. Now, if I substitute this limits k lambda by a sin theta 2 minus sin minus theta 1. Sin of minus theta minus sin theta. So the result would be E perpendicular k lambda by a sin theta 2 plus sin theta 1. I am writing it as sin theta 1 plus sin theta 2. Makes no difference. Very, very, very important formula for the vertical component, perpendicular component of the rod. Same steps goes here as well, but for parallel component. So DE, we already know what is DE. So I'm going to write the equation DE parallel, DE, right? DE we already know. What is DE? K lambda by a d theta, before that sin theta d theta. I'm going to apply the integration. Again the angles goes from minus theta 1 to plus theta 1, plus theta 2, minus theta 1 to theta 2 plus theta 2. So, and this entire term will be E parallel. E parallel. K is constant, lambda a. Sin theta will be, sin integration of sin theta is minus cos theta, and the limit goes from minus theta 1 to theta 2. As we know, cos theta is an even function. Cos of minus theta is again cos theta. So what am I getting finally? K lambda by a minus can be taken out. Okay. Now cos theta 2 minus cos theta 1 minus theta 1, of course. So E parallel, cos of minus theta is cos theta again. So what am I getting? If I multiply this negative sign k lambda by a, if I multiply this negative sign cos theta 1, negative sign cos theta 2. So this is the expression for the parallel component of electric field due to a charged rod at a point perpendicular to the rod. Okay, so I hope the steps that I followed are very much understandable, very clear to you. Okay, if you still feel any difficulty in understanding, please watch it again for multiple times. You will be able to understand it for sure. Okay, okay, let's recall, repeat the steps again for one more time. So I have taken a charged rod, I have considered a point of interest P, and I have divided this entire rod into small piece. I have considered one piece whose length is dy, whose charge is dq at a distance y from the vertical line. Now the electric field due to this charged element is dE. I've written the expression for dE like this. I've got these two expressions by using the triangle, this one. Okay, now I have taken two components. DE has two components. One is perpendicular to the rod, one is parallel to the rod. Perpendicular to the rod is DE cos theta, so which I have analyzed, and parallel to the rod is DE sin theta, which also I have analyzed. I have got the final expression for the perpendicular component and parallel components of the electric field due to the charged rod at a point on the line perpendicular to the length of the rod. Okay, right. The key points here are, remember, if I have already measured these angles theta 1 and theta 2 according to the direction of measurement. Okay, our reference line is this one, vertical to the rod, perpendicular to the rod. We are measuring the angles from the line perpendicular to the rod, okay, and angle measured below the perpendicular to the rod are to be taken negative, above the perpendicular to the rod are to be taken positive, which we have already taken. If you take, while solving the problems, if you take the negative sign again for this angle, you will get the wrong result. Okay, this negative sign we have already used in the analysis. Let's say instead of measuring this second ends angle in the below the axis, you are measuring it above the axis. In such case, you need to mention positive sign. I have the examples. I'm going to discuss the example as well, so that you will be able to understand how we need to consider the angles, whether we need to take the positive angle or a negative angle, that you will be able to understand in the further examples. Okay, let's look at the example. Next example. Uh, okay, right. We have the example here. So let's define the example. Okay. Let us suppose I'm drawing the lines. Okay, let this angle is let's say 30 degrees, and this angle is 60 degrees. Let's suppose 60 degrees. Okay, now here we have linear charge density is lambda that I'm taking, and this is again A. Okay, now E perpendicular is equal to k lambda by A sine theta 1 plus sine theta 2, sine theta 1 plus sine theta 2, right? Now whole into, as I know sine theta 1 is 30 degrees. We are measuring this angle below the vertical line, reference line. But while we are deriving this equation, we have already used the negative sign. If we use the negative sign again, will give us wrong results. Okay. So what I'm going to do is I'm going to use this angle as it is. K lambda by A sine 30 plus sine 60. Sine 30 plus sine 60. What am I getting? E perpendicular is equal to K lambda by A sine 30 is 1 2 plus sine 60 is root 3 2. Okay, k lambda by 2a 1 plus root 3. So this will be the perpendicular component. This will be the perpendicular component. Now coming to the parallel component, I have the parallel component E parallel is equal to k lambda by a cos theta 1 minus cos theta 2, cos theta 1 minus cos theta 2. Similarly, here theta 1 is equal to 30 degrees, theta 2 is equal to 60 degrees. And substituting the quantities here, k lambda by a, sorry, cos theta 1 is 30 degrees, cos theta 2 is 60 degrees. Okay, k lambda by a, cos 30 is root 3 by 2 minus 1 by 2. What am I getting? K lambda by a 2 root 3 minus 1. E parallel. So I've got E perpendicular and E parallel. You can even find E net. E net is nothing but root over, both are perpendicular to each other. So the result will be E perpendicular square plus E parallel square. Remember this formula as well. E perpendicular square and E parallel square to find the total electric field at the point of interest. Total electric field at the point of interest. Okay, right? Clear? Now let's look at one more example. One more example. What is it? There is no line. Okay, let's look at one more example. Okay, now what I'm going to do is, let's define the question. I have taken a point somewhere here, somewhere here. Okay, at a distance here, at a distance A. Now the one end of the rod is making, sorry, one end of the rod is making an angle 30 degrees, an angle 30 degrees, and we have this angle 30 degrees again, 30 degrees again. Now I asked you to find the electric field, net electric field at point P, perpendicular and parallel electric fields. We know how to find the net electric field, right? Okay, so electric field at this location. It's quite easy. Okay, right. Now, as I've already told you, the distance A, the distance A that we have taken in the example. Go back to the previous lectures. Okay, see, the A that we have taken is perpendicular to the rod. Perpendicular to the rod. Is my point clear? Now, the A that we have taken should be perpendicular to the rod only, right? That means I have to find this distance. This distance I have to find, right? I have A here and 30 degrees angle here. What will be the adjacent? It will be A cos 30 degrees, right? A cos 36. If I consider this as a right angle triangle, then this will be our adjacent. To find the adjacent, what trigonometric function that we use? Cosine. So A cos 30. Okay. I have found the perpendicular distance from the rod. From the rod. A cos 30. Okay. Now, linear charge density of the rod is lambda. Linear charge density of the rod or wire or anything. Line charge is lambda. Then E perpendicular is equal to E perpendicular is equal to K lambda by A is what? A cos 30 degrees. A cos 30 degrees. Hope my point is clear. Hope my point is clear. Right? Okay. Now, cos theta 1, cos theta 2. Now, let's identify theta 1 and theta 2. Theta 1, theta 2. As I've already told you, I have measured the angle theta 1 below this vertical line. Below this vertical line. So, I have taken negative sign already. Negative sign already. Instead of measuring it in downward direction below this line, if I measure that angle above that line, do I have to take the positive sign or negative sign? This time it will be negative sign, because I have measured the angle in the below the line. I have taken negative. Above the line I have taken positive. Already that I have taken. Already, which are there in the formulas. Which are there in the formulas. Sine theta 1 plus sine theta, right? Which are there in the formulas. Instead of going below, let's say this time I'm going above. Angle that I am measuring from the perpendicular line as reference, this angle is to be measured in opposite direction, right? Or else I have to go all the way from here to here, which will be 270 degrees or minus 30 degrees or minus 30 degrees. I'm going down. I'm going down. I'm going down. I'm going down. The line I'm not, getting. Here I've got the line. So the angle that I've turned to find this line is 270. Is 270. You can use 270 degrees, or you can use minus 30 degrees. Minus 30 degrees. So theta 1 can either be theta 1 can either be minus 30 degrees or 270 degrees. 270 degrees. Now coming to theta 2 angle. Theta 2 angle I am measuring from this reference line is this one only, no? Perpendicular to the length of the rod. From here to here, this will be our theta 2. This will be our theta 2. Theta 2 is how much? 60 degrees. Theta 2 is how much? 60 degrees. Is my point clear? Right? Okay. Now, as I know theta 1 and theta 2, I can directly substitute these two in the formulas. E perpendicular is equal to K lambda A cos 30 is root 3 by 2. Root 3 by 2. Sin theta 1 is minus 30 degrees, plus sin theta 2 is 60 degrees. Okay, whole into. What am I getting? Sin minus 30, no, sin 60 is root 3 by 2. Sin minus the minus 1 by 2. You can take 2 common, 1 by 2 common, and this 2 will get cancelled. What are we left? K lambda by root 3a. Here we have root 3 minus 1. Root 3 minus 1. E perpendicular is equal. Similarly, we can find E parallel as well. So E parallel is equal to K lambda by A cos 30 degrees into cos theta 1 minus cos theta 2, right? So K lambda by A cos 30 is root 3 by 2. Cos theta 1 is cos minus 30 degrees minus cos 60 degrees. Cos of minus theta, cos theta again, even function. So what will be the answer? Uh, 2, sorry. Okay. So cos 60 is 1 by 2. Cos 30 is root 3 by 2. Even though it has minus 30, Cos minus theta is cos theta, so I'm taking it as root 3 by 2. So these 2's will get cancelled, k lambda by root 3a, and we have root 3 here and minus 1 here. E parallel is equal, and we know what is the net field. E net is equal to E perpendicular square plus E parallel square, and in our case both of them are same. Both of them are same. Hope the steps that I followed are very clearly understandable. The only clarity that you need to get is how to take the angles. In the example that I've taken, the angles were measured from the vertical line. Below are taken as negative, above are taken as positive, which are being already analyzed. And by using such sign conventions, we have already obtained the formulas. Again, we using the negative sign. If we go below, will give you wrong results. If we are measuring the angles against to the direction that we have considered are to be taken as negative. See, let's say I have obtained the formulas by taking the negative signs for the angles measured below the reference axis. Okay, if you use the same negative sign again, it will give you wrong results, right? Let's say I've been measuring the angle above the reference axis. In such case, instead of measuring the below, measuring the angle below, you need to consider the negative sign, because it is against to the direction that we have considered. Okay, so negative sign that I've taken. Or else, instead of avoiding this confusion, you just start at the vertical line and draw the angle like this. Wherever you find the line, you measure the angle, you substitute it directly. You can use 270 also. If you use 270 also, you'll get the same results, right? Okay, let's move on to the next example. What is it? Okay, electric field due to infinitely long charge wire. So in the earlier case, the wires or the rods are finitely long. They have certain finite length. Okay, but in this case, the rod or the wire is infinitely long. The term infinity is a relative term. Can I say this this pen this pen is infinitely long? Do you agree that this pen is infinitely long? Yes, it can be infinitely long, depending on the point that you are considering. If you are considering the point here, which is point means teeny tiny point, okay, here, then the length for this point, the length of this pen is infinitely large. Let's take the point somewhere here at this distance. For this point, this length is finite. So that's why I'm saying this infinity or infinite long is a relative term. Anyhow, I've taken an infinitely long charged wire. Now what I'm going to do, I'm going to find the electric field due to this infinite long charged wire. Now let's take a point somewhere here. Okay, which is at a distance a. Let it be like that we have taken in the earlier examples as well. Okay, as this wire is extended to infinity, this is not the end of this wire here, it is extended to infinity. If we consider the point here, the angle is this one. If we consider the point here, the angle is this one. If we consider the point here, the angle is this one. As we go above to infinity, the angle keep on increases. If it is extended to infinity, it is very large, it is at very large distance. The end of this wire is very large distance from this point. In such case, can I consider the angle is close to 90 degrees, which is theta 1 is equal to 90 degrees. Can I consider theta 1 as 90 degrees? Yes, of course I can consider it as 90 degrees, nearly 90 degrees. And can I consider, because this end also extended to infinity from this point, I can consider this end also, theta 2 also 90 degrees? Yes or no? I'm going to explain this point again. I have considered this point from the infinitely long wire, charged wire. Okay, at distance here, let it be. As the wire is extended to infinity, let us suppose wire is still here, then the angle is very less. As wire is increased, then the angle has increased. If wire is further increased, then the angle also further increased. If the wire is increased to infinity, wire is increased to infinity, then the angle could be reaching to 90, almost 90. So I can consider theta 1 as 90 and theta 2 also as 90 because the other end also extended to infinity. So as I've got theta 1 and theta 2 and linear charge density of the wire is lambda, in such case I have this E perpendicular, which is k lambda by a sine theta 1 plus sine theta 2, which we have already learned in the earlier slides. So k lambda by a sine 90 plus sine 90 plus sine 90 sine 90 plus sine 90 degrees. This is 1, this is also 1. What am I getting? 2k lambda by a, which is E perpendicular. Now let's see what happens to E parallel. E parallel. E parallel. E parallel formula is k lambda by a cos theta 1 minus cos theta 2. Okay, so E parallel is equal to k lambda by a cos 90 minus cos 90. Both of them are 90, right? Cos 90 is 0, cos 90 is again 0. So 0 into anything is 0. E parallel will be 0. There is no E parallel component for the infinitely long charged wire. Infinitely long charged wire. So the electric field due to an infinitely long charged wire is sorry is along the perpendicular to the length of the rod only. Perpendicular to the length of the rod only. E perpendicular. And if you want to find the net field, as E parallel is 0, E perpendicular only, E net. E perpendicular only, E net. I'm going to write the formula again. E net of infinitely long charged wire is nothing but E perpendicular equation, which is 2k lambda by a. 2k lambda by a. Hope the steps that I followed are very much clear and understandable, right? Okay. Let's look at another example. Yeah, this is also an infinite charged wire. Infinite long charged wire. Charged wire of linear charge density lambda, let it be. Okay, now let us define a question here. Okay, it is a very good question, little bit lengthy, but anyhow it is a very good multiple concepts questions. Okay, right. Okay, now I'm going to take a charged particle. I'm going to place this charged particle initially somewhere here. This is an infinitely charged long rod. Okay, so somewhere here. Its initial length is R1, let it be. Its initial length is R1. Very good question. Just follow the explanation that I'm doing here. Okay. So R1 distance. Linear charge density of the rod is lambda. Okay. Right. And we know the electric field due to infinitely charged rod is 2k lambda by A. 2k lambda by A. Okay. Now, I have taken a charge Q and mass M. Mass M. Particle of charge Q and mass M. I just left it free. I just left it free. Left it free from rest. Left it free from rest. Initially at rest. Initially at rest. U is equal to 0. U is equal to 0. Clear? Okay. Now the question is, what is the now the concept is, if I leave this charged particle, does it move or not? It will definitely move, because let's say this is positive charge and field at this location will be away from the positive charge, that too along the perpendicular line, as I've already learned in the earlier example. Parallel component is 0. parallel component is 0, we will get only perpendicular component. So the field is perpendicular to the rod in this direction. Okay, as field is in this direction, I have placed a positive point charge in the field. It will move in the same direction as that of the field, right? Okay, now, and if you are unable to follow this, let's go with blind point. That is, this is positive charge, this is positive charge. It will repel this positive charge as the field is along the perpendicular direction, perpendicular axis. It will move along the perpendicular axis only. Okay, right. Now it starts to move. It accelerates. It accelerates. Okay, it accelerates. That we have understood. That we have understood. It is accelerating. But the field varies with distance. The field varies with distance. That means force also varies with distance. That means force is not constant. Follow the points. As the distance increases, the electric field strength decreases. A increases, field decreases. As the distance increases, electric field strength decreases. As the electric field decreases, electric force also decreases, because F is equal to EQ. F is equal to EQ. As E decreases, F also decreases. Q is not changing. Q is not changing. Okay. So as the force is decreasing, the acceleration also decreases. F by m. Acceleration also decreases, right? That means acceleration is non-uniform. Acceleration is non-uniform. It may appear like we can use simple kinematic equations to solve it, but it is not as that simple as you are thinking. Okay, because the acceleration is not constant, you cannot use the kinematic equations like v is equal to u plus at, s is equal to ut plus r, v square minus u square equal to s. We cannot use such simple equations. Rather, we are going to use work energy theorem instead. Okay, so acceleration is changing. Okay, now the question is, let us suppose this charged particle has reached a point here, okay, which is at a distance r2, which is at a distance r2. Now the question is asked, what is the final velocity of the charged particle by the time it reaches to the point r2? Point r2. Hope the question is clear. Hope the explanation is clear till now, right? Okay, as I've already mentioned, we cannot use the simple kinematic equations, as acceleration is non-uniform, that is not constant. So instead, what I'm going to do is I'm going to use work energy theorem. Work energy theorem. What is work energy theorem tells us? Work energy theorem. Work done by all forces, work net, is equal to change in kinetic energy. Change in kinetic energy. So work done by all forces, in the sense only one force is acting here. Gravity, that I have ignored. Gravity is ignored. Gravity is, sorry, gravity is ignored. So sorry, gravity is ignored. Gravity is, so only one force is left, that is electric force. Work done by electric force is equal to kinetic energy final minus kinetic energy initial. Change in kinetic energy. Okay. Work done by electric field. Work done by electric field, which is not constant. Work done by variable force. So integral electric force into dx is equal to half mv square minus half mu square. Half mu square. As I already know, u is 0. Initial velocity, the particle is released from rest, so initial velocity 0, kinetic energy initial is equal to 0. I have used this formula half mv square, which is the formula for kinetic energy. Final velocity I have used for final kinetic energy, initial velocity I have used for initial kinetic energy. As initial velocity is 0, so initial kinetic energy is to be taken as 0. Okay, now what is electric force? Which is nothing but EQ. EQ dx is equal to half mv square. Half mv square, right? E, electric field due to this element. Let us suppose consider a point. Consider a point somewhere here at a distance x. At a distance x. Now, electric field at a distance x is 2k lambda by x. 2k lambda by x. 2k lambda by x. Instead of taking a, I've taken x because I'm considering the distance as x. Okay, into q. E I have already written into q. Force into dx is equal to half mv square, half mv square. Okay, now how does the position is changing here? The x value is changing, right? Particle is left here and it is moved till, sorry, particle is left here and it is moved here, right? So the initial position is r1 and the final position is r2. It may not be the final position, it may be moving further, but in our case it is the final position. Okay, so r1 and r2. So k, q, lambda q are constant. 2 k lambda q are constant. 1 by x integration is lambda log x. Integration of 1 by x is log x, and it is ranging from r1 to r2 is equal to 1 by 2 mv square. 1 by 2 mv square. 1 by 2 1 by 2 mv square. 1 by 2 mv square. Okay, now so if I want to rewrite this equation, how do I write it? 2 is here, 2 is here, this 2 can be multiplied. 2 into 2 4 k lambda q, 4k lambda q, and this m can be taken this side, m 4k lambda q m by m. Okay, and log r2, log r2 minus log r1 is equal to v square, is equal to v square, right? Right? Okay, now this log a minus log b can be written as 4k lambda q by m is equal to log r2 minus log r1. Log a minus log b can be written as, sorry, not is equal to, into log a by b, that is r2 by r1 is equal to v square. If I want to take out this square, if I want to take out this square, I have to put a root here. I have to put a root here, right? Now the final velocity acquired by the charged particle that we have taken is 4k q lambda by m log r2 by r1 under root. So this is the formula, not the formula, equation for the velocity acquired by the charged particle by the time it reaches the distance r2. R2. It is a very good example. It is a multi-conceptual question where it involves linear charge density, electric force, and then work energy theorem. Combination of three different concepts. Okay. So I hope this entire example is clearly understandable. If you are able to follow it, please do not forget to like, share, and subscribe. Okay, right. Let's move on to the next example. Okay, electric field due to semi-infinite charged wire. Electric field due to semi-infinite charged wire. Okay, right. So semi-infinite charged wire. That means the length in this direction is infinity, length in this direction is finite. So I'm taking the point here at this location, okay. Now if you go away from this line, the angle keep on increases, as this wire is extended to infinity, this angle will be 90 degrees. This angle will be 90 degrees. This angle will be 90. Theta 1 is 90. Theta 1 is equal to 90. How about theta 2? How about theta 2? In our case, I've taken the line here. In our case, theta 2 is 0 degrees. Theta 2 is 0 degrees because there is no rod in the below. below this line. Okay, even if I go round like this, it will be 360 degrees, makes no difference. Even if you take 0 degrees or 360 degrees, you will get the same results. Okay, so theta 2 is 0 degrees. If I use same equations like E perpendicular, k lambda by a sine theta 1 plus sine theta 2. Okay, E parallel is equal to, sorry, k lambda by a cos theta 1 minus cos theta 2. Cos theta 2. Now use the angles that we have identified for this, finite wire. So k lambda by a sine 90 plus sine 0. Okay, and E parallel, which is k lambda by a cos 90 minus, sorry, theta theta 1 is not, okay, sorry, this is not theta 1, this is theta 2, theta 2, and this is theta 1. So I'm going to erase all these things. Okay, 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 right. Now let's write these equations. E perpendicular is equal to k lambda by a sine theta 1, theta 1 is 0, sine 0 degrees plus sine 90 degrees. Okay, E parallel also I'm going to use the same angles, k lambda by a cos 0 degrees minus cos 90 degrees, right? Okay, sine 0 is 0, cos 90 is also 0, and sine 90 is 1, cos 0 value is again 1. E perpendicular, E perpendicular, what am I getting for E perpendicular, which is k lambda by a, k lambda by a, k lambda by a, because this is 0, this is 1, k lambda by a. E parallel also I am getting k lambda by a, this is 1, this is 0, k lambda by. If you want to find the net field, E net is equal to what? E perpendicular square E parallel square under root. What you will get? K lambda by a whole square, k lambda by a whole square, which will be root 2 k lambda by a, root 2 k lambda by a. Okay, for a finite wire, it is not always necessary for this line to be considered exactly at the bottom point of the line, wire, charged wire. Sometimes the line can also be considered something like this. If we have this wire extended to infinity, you can even consider the point somewhere here as well, and this angle need to be finite. Let us suppose 30 degrees or maybe 60 degrees, sometimes it may be 45 degrees. Okay, such case also can be used. We will discuss this kind of example in the later slides as well. Okay, you don't have to worry about it. I hope this electric field due to a finite charged wire is clear to you. Is clear to you, right? So angles that we have identified here, right? Theta 2, 90 degrees. Angle above measured is theta 2, below measured is theta 1 in the first electric field due to finite charge. So theta 2 is 90, theta 1 is 0 degrees. Theta 2 90 because this wire is extended to infinity. The angles keep on increases. It becomes nearly reaches to infinity. So I'm taking it as 90. And as there is no wire below this line, I'm taking it as 0. Even if you want to go to measure the angle continuously, so go measure the angle and till you reach the line, reference line. Okay, you will get 360 degrees. You can use 0 degrees or 360 degrees, both of them will give you same result. Okay, the result will be k lambda by a, and again k lambda by a. The net electric field at the given location is root 2 k lambda by a. Okay, let's look at the next example. Right. Okay, this is a very good example. It's not an easy one, uh, but anyhow it is a combination of finite charged wires. Okay, let's define the question first. Let's consider a point here. Okay, this is point P, which is at angles, this is a. Okay, that means this angle is 45 degrees, this angle also 45 degrees, 45 degrees and 45 degrees, and these two wires are semi infinite wires, semi infinite, infinite, semi infinite. This is also semi, sorry, semi infinite, semi infinite, semi infinite. Okay, clear? Both of them are semi infinite wires. As I've already told you in the earlier example, we have taken the point exactly at the bottom line, right? But in this case I haven't taken the line exactly at the bottom, rather I have taken the line exactly the bottom is making 45 degrees from the point of interest. Okay, right, semi infinite wire. Okay, I'm going to divide the entire system into two parts. Entire system into two parts. First one is vertical line charge. Vertical line charge extended to infinity. And here the point that we have considered is somewhere here. And this is angle 45 degrees. Angle 45 degrees. Okay. Now, this E perpendicular and this E parallel. Clear? E perpendicular, E parallel. Okay. Now I'm going to take the another wire, which is this one, and it is also extended till infinity. Point is considered somewhere here. It is making 45 degrees again, right? So, as both of them are positive, I'm considering them as positive. Field is away, perpendicular, E perpendicular, and E parallel. E parallel is in this direction. E parallel. E parallel. The parallel components are not towards the infinite points. Okay, they rather towards the finite points, finite end of the rods. Okay, okay. So E parallel. Now let's find E perpendicular to E parallel to E perpendicular 1, E parallel 1. Okay, let's find E perpendicular 1. Okay, right. Now E perpendicular 1. E perpendicular 1 is equal to E perpendicular 1 is equal to, we already know, k lambda by A. I have already mentioned A, sin theta 1. Sin theta 1 is how much? Theta 1. Theta 1 is infinity, right? 90 degrees. 90. Theta 1 is 45. Sin 45. Sin 45 degrees plus theta 2 is 90 degrees. Theta 2 is 90 degrees. Sorry. Theta 2 is 90 degrees, right? Right. So E perpendicular 1 is equal to sin 45 is 1 by root 2, sin 90 is 1 plus 1 by root 2, k lambda by A 1 plus 1 by root 2. Okay, this is perpendicular, and E parallel 1 is equal to k lambda by A cos theta 1. Cos theta 1 is how much? 45. Cos 45 is 1 by root 2, 1 by root 2 minus minus cos 90. Cos 90 is 0. Cos 90 is 0. Cos 90 is 0. And coming to the next case. Okay, E perpendicular 2 is equal to k lambda by A. K lambda by A. Lambdas that we have taken, linear charge density lambda, linear charge density lambda, k lambda by A. K lambda by A. Okay, Again, the angles. Theta 1 is 45, cos, I mean sin 45 is 1 by 2, and in this direction it is 90 degrees, 90 degrees, parallel component. Okay. Now, theta 1 is 45, theta 2 is 90 degrees. Theta 2 plus 90 degrees. Sin 90 is 1. Sin 90 is 1. Right? E perpendicular to sin theta 1, 1 by root 2, 1 by root 2 plus sin theta 2, 90 degrees. Okay. Now, E parallel to, E parallel to, which is K lambda by A, K lambda by A cos 45. Cos 45 is how much? Cos 45 1 by root 2, cos 45 1 by root 2 minus 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 cos 90, minus cos 90. Cos 90 is how much? 0. Cos 90 is how much? 0. I hope that steps that I followed are clear to you. I'm using the direct steps because we have been discussing these two formulas since 5 or 6 slides, right? So it will be, I think you might remember those formulas till now, right? Right. So angles that I've considered here, I'm taking theta 1 is equal to 45 degrees, theta 2 is equal to 90 degrees, and here I am considering theta 1 is equal to 45 degrees, theta 2 is equal to 90 degrees again. So what am I getting? 1 by 2, 2 minus 0. Okay, right. So I know the directions. I'm representing the vector notation as well. Okay, right. This is positive I cap, positive I cap, and this is negative j cap, minus j cap. Okay. Now this is E perpendicular to is positive j cap, positive j cap upwards, and this is negative I cap, negative I cap. Let's say E net, E net vector representation. E net is equal to add all the vectors, add all the vectors. So k lambda by a, k lambda by a I cap, I'm multiplying all this, k lambda by root 2 a I cap. I've wrote this expression into two expressions, and then this expression minus k lambda by root 2 a j cap minus multiplied before the expression, and here we have plus k lambda by root 2a j cap, root 2a j cap plus k lambda by a j cap, k lambda by a j cap, and then I am left with one more expression, which is minus I k lambda by root 2 a I cap, root 2 a I cap. Okay, right. Now if we have the similar terms with opposite sign, they get cancelled out. K lambda I, k lambda by a I, there is no such a term. K lambda by root 2 a I cap plus k lambda by root 2 a I cap minus, these two will get cancelled, and minus k lambda by root 2 a j plus k lambda by root 2 a j, these two will get cancelled, and I left with only two expressions. What are the expressions? E net, sorry, E net in vector form is equal to k lambda by a I cap plus k lambda by a j cap in vector notation. If you want to find the magnitude, you can easily find it, right? E net vector. What will be the magnitude? E net is equal to E x square plus E y square, perpendicular components. E x is nothing but k lambda by a whole square, and Ey is also k lambda by a whole square under root, what am I getting, root 2 k lambda by a. E net is equal to E net magnitude is equal to. This is not a simple example, not I mean it cannot be easily solved, but anyhow, if we know the basic concept of semi infinite wire, charged wire, then it is easy to find the net field due to both the semi infinite wires. Okay, so this is a very good question. If you are able to follow it, very good. If you are unable to follow it, just watch it again. If you are still unable to follow it, please comment below. Okay, so I hope the video is helpful. If you really find the video is helpful, please do like, share and subscribe, and don't forget to hit the bell icon in order to get the notifications as soon as I upload the videos. So that's it in this video. Thank you for watching. See you in the